2. Frequency distributions. We are going to now build on what we talked about last time. So in this next hour, we are going to talk about things like frequency distributions and how to organize data into frequency distributions in both group frequency and simple or individual frequency distributions, how statisticians interpret those frequency distributions, or how we interpret those data sets, and how we organize them into graphs that we can then talk about and help us understand them better. Things to keep in mind. So in the previous lecture, we talked a lot about scales of measurement. So think back to nominal, ordinal, interval, ratio. Also really keep in mind concepts like continuous and discrete variables. And then also that idea of real limits, right? So numbers having things like upper real limits and lower real limits. Some of the concepts that we're going to introduce or kind of build on a lot more in this lecture is fractions, decimals, percentages, and then again interweaving how we build tables, not just for numbers, but also concepts that are more nominal and ordinal in nature. Okay, so what is a frequency distribution table? It's a way we can organize into a tabulation. It does show numbers of individuals located on each category on that scale of measurement. It can either be a table or a graph. And again, you, the statistician, you, the researcher, you, the scientist, get to determine, based on what kind of data you're using, how you want to display your data. Also, a frequency distribution always shows the categories making up original measurements and the record of that frequency, or the numbers of the individuals in each of those categories. Okay. So some of the things you need to keep in mind. 1, the structure of frequency distribution table has categories in the column, right? So, and normally it's ordered or structured from the highest to the lowest. You're always going to be able to find out the frequency count, and it's going to have that beautiful kind of slanty F. And next to a category, and that's designated or notated by an X. This is our first formula that we're introducing in this series of videos, and it's sum of F equals N, capital N. And to compute sum of X, or the sum of scores, we're going to use this table, right? So what we do is we convert the table back to the original scores to help us compute that sum of X, or the sum of F of X. Okay. So to get into some more terms and definitions, we're going to talk about proportions and percentages. So proportions, and I'll just read this, measures the fraction of the total group that's associated with each score. So as we talked about in the last lecture, a score or a datum is that one identifiable characteristic that one of your people produces or that you record off of your participants, right? So proportion is going to measure that fraction of that total group. A percentage expresses that score, right, relative to the frequency out of 100. Okay, so percentages will never exceed 100. So the equation you're looking at for proportion is proportion equals P, and again, it's going to be more of like a slanted or a cursive P, equals F divided by N, capital N, notating a population. The percentage then is P times 100 equals the frequency, right, how often, divided by N, the total number of people in your population, times 100, right? So a proportion can also be called a relative frequency because they describe the frequency in relation to the total number of people that you have in that population. And the percentage, therefore, can be included as the separate column in each of the frequency distribution tables. So I know this is a lot of terms, and it's going to make a lot more sense once I can show you what it looks like in that table. Okay, so let's take a look at what's included in a frequency distribution table. So over on the far left-hand side, you can see we have the raw scores. So say you pull a group of 5 people for your study. Okay. and they have the opportunity to score a 0, right? Say they have an opportunity to score a 1, a 2, a 3, a 4, and a 5. Maybe you're measuring how high they can jump in inches, right? You can jump 0 inches, right? You can clear no air at all. Maybe you're measuring like third graders in your third grade class. And then you have one third grader that can jump 1 inch, right? They barely skim right the floor. Okay. If you notice on the raw scores, right, we start at the very bottom, the lowest amount, right? And so in this case, the little third graders that can't jump any, but you didn't have any of those. You had one third grader that only could jump 1 inch. Now you say, I wonder how many of my third graders jumped 2 inches, and you actually didn't have any. Now, in statistics, you have to record 0 because 0 is a score, is a record. You need to record that. It's important to know that you had 0 third graders jump 0 inches or 2 inches. Okay, so you record 0 for 2 inches. Then if you take a look at the frequency of your third graders that jumped 3 inches, you actually had 4 third graders, right? So you write down 4. And then how many of your third graders jumped 4 inches? Well, you had 3 of your third graders do that. So you tally down 3 and you write down 3. And then your really, really tall jumpers, right? The ones that, I don't know, wore their special magical shoes and I don't know, they're your tall jumpers, right? And they only had 2, right? So you had 2 of them jump 5 inches, okay? So your raw scores, this is like your possible inches they could jump, right? Your frequency, that's your X. Your frequency is your F. That's your tally, that's your count, okay? The proportion then, how you get that is the relative frequency divided by your total number of people that you had in your class, your third graders, okay? So if you add up your total number of people in your class, so you say I had 2 people that jumped 5 inches, and I had 3 people that jumped 4 inches, and I had 4 people that jumped 2 inches. I didn't have anybody that jumped 2 inches, and I only had 1 person that jumped 1 inch. Well, I have 10 third graders during this recess that jumped. That let me measure their jumping ability. Okay. So you say, I can't have anything besides 100% because everything always adds up to 100%, right? So I say 2 divided by 10 because that's my number of people I had, my third graders. And I can also say, so my proportion is 0.2%, or if I want to say percentage, I would then say 20%. And I can keep doing that for each one of my categories there. And I could say, well, I wonder what proportion or what percentage of my third graders jumped 4 inches. Well, I would take 3 because I know I had 3 of my third graders jump 4 inches. And I would say 3 divided by 10, well, 0.3 proportion or 30%. And I would keep going. I can keep filling in it, that table, right? And if you take a look at 0, because again, 0 is a real number, 0 needs to be recorded. I had 0% of my third graders jump 2 inches. Okay. So this is just a simplified version of this frequency distribution table. Can you tell me how many subjects were in this study? And the simplest way to determine this is I add up my F's. I add up 2 plus 4 plus 1 plus 0 plus 3. Because my F's are my count, my F's are my frequency, my F's are my occurrences. Okay, another learning check. For the frequency distribution shown, is each of these statements true? True or false? More than 50% of the individuals scored above 3. So I'll repeat that. More than 50% of the individuals scored above 3. Number 2, the proportion of scores in the lowest category was proportion equals 3. The proportion of scores in the lowest category was P equals 3. Okay, so this one's a mixed bag. Let's break this down. So when I say, go back up one zoom, right, more than 50%, that is true, right? Because 6 scored above 3, right? Because I know, if you go back to our third grader example, 2 of my third graders jumped 5 inches or higher, and 4 of my third graders jumped 4 inches or higher. So that's 6. 6 is 60%. Okay. Now the next one's a little bit tricky. Okay, this is where it gets a little bit like, right? It's not 3, but proportions are always reported, right, in decimals, right? Percentages are always given with a percentage afterward, but proportions are always delivered in decimals. So it's 0.3. Okay. Histograms and polygons are used when we want to demonstrate or to report or to show data measured on either interval or ratio scales. Okay. Yes, we do have 2 axes. The x-axis has categories of measurements on from left to right, and the y-axis has frequencies increasing from the bottom to the top. Okay. Ideally, you should have both those axes come together or converge at the bottom left-hand corner at 0 where they meet. And I'll show you what that looks like in a second. You're going to list all numeric scores on the x-axis, and you're going to draw bars above each class interval. And yes, I will show you what that looks like in a second. Please remember that the height of the correspondence should correspond to the frequency, so that you count how often it happens. And the width of the bar should correspond to the real limits. Again, think upper and lower real limits. For a continuous variable, the score recorded corresponds to an interval on the number line rather than a single point. For a grouped frequency, the apparent limits are demonstrated. Okay, so let's go back to continuous. So with a continuous variable, sometimes an individual with the same recorded score might have a different actual measurement. Okay. This is hard, but it's usually hard to understand. And it's not that the statistician is lying, but it's usually because either you're dealing with like a very, very large population, so like you're usually dealing with with grouped frequency, or with continuous variables, it kind of like goes and it slurps over to the other side, or it melts into the other side. Okay, so a frequency distribution table, the scores, and I put that in quotes on purpose, right? It really is more referring to the interval's real limits, or how much it expands out. Okay, so I know we touched on, actually we hit pretty hard, real limits in the last lecture. So if you take a look at this one, if I'm going to do weight of, I don't know, 5th graders, 7th graders, I have no idea how much little kids weigh. Okay. If I take someone's recorded weight and I say Sally weighs 72 pounds and Marcos weighs 74 pounds, they're going to be put in the same category of 72 to 75. And so when I say there's 5 kiddos that are kind of in that group, I'm going to go back one slide. So top right-hand corner where it says like individuals with the same recorded score might have different actual measurements. That's what we're talking about here. It's not that we're lying. It's just that sometimes we're dealing with such large numbers, or it doesn't make sense to break it down like so far down into like individual numbers that we start grouping them together. Okay. Another way we do this is like with grades, right? So not at a lot of colleges, but some colleges have it where you have like 94 5 to 100 is an A plus, or like 97 to 100 is an A plus, and 96 to 92 is an A, and 90 to 91 and 92 is like an A minus, right? And then some colleges have it where 90 to 100 is an A. Well, the problem with having 90, 100 as an A, that's a huge grouping, right? Or like 80 to 90 being a B. That's a big difference in a student's like production of work. But on the transcript, it just says B, right? So you do lose a little bit of definition. You do lose a little bit of clarity whenever you just have like a bigger grouping, but it makes reporting a lot easier. It makes, telling people data a lot easier. Okay. So what are the apparent limits for a score of 73? Well, the apparent limits are really anything that you consider like 72 all the way up to 75. And really, when we get down into it, it's anything that's 71.5 or 49999. So anything that crosses that bar up until that upper, or anything that's the upper lower, or the lower real limit, upper real limit. Usually we refer to this and use this one when there's lots of data. Like we mentioned in the previous lecture, you know this, at least on a theoretical level, because if you have an 89.5% in that English class, you're fighting for that A, because it feels a lot different than an 89.4 because of the rounding up factor. Okay. Quick learning check. A group frequency distribution table has categories 0 to 9, 10 to 19, 20 to 29, 30 to 39. What's the width of the interval of 20 to 29? This one's, it's going to seem like a trick question to you, but it's not after I explain it to you. It's actually 10. Okay. I don't advocate counting with your fingers a lot, but I'm going to count my fingers just the one time. Okay. When we say things like 0 to 9, 10 to 19, 20 to 29, 30 to 39, think back to when I said 0 is a real number. 0 means something to statisticians. If your participants give you a 0, you have to record it. Think back to that. Okay. The width of the interval, 20 to 29, is 10 and not 9, because if somebody gives you a score of 20, you have to count it. Okay, so let's count it. 20, 21, 22, 23, 24, 25, 26, 27, 28, 29. I know your brain doesn't like that. Visually, you don't like this, okay? And you don't like it right about here, right? 20, you're fine with, because you understand intellectually 20 is a score, right? So if I say, okay, I'm going to take my 9th grade science class out to the beach, and we have to collect seashells. And then I'm going to say, okay, you have 1/2 hour, and come back, and we're going to make a histogram on how many we were able to collect in that 1/2 hour. And some of my little 9th graders are not going to come back with any seashells, right? Like they're just like going to miss the question, or they're not going to be able to understand it, right? So some are going to have 0. Some will get 7, and some will get 9. Some will get 4. So everybody in that category will be into 0 to 9. We're then going to have another group that will get 10 to 19, 20 to 29, and 30 to 39. If you are that little 9th grader that gets 20, you do count, right? So you understand 20 is a legitimate number and you'd be counted. So your brain is fine with 20. Right about now, or hold on, so you're fine with 20, 21, 22, 23. This is where your brain starts to freeze. 24. Your brain isn't like that, right? Because this looks like 5 to you, because I have 5 digits holding up. and your brain really doesn't like this, 9. It's okay. Build a bridge and get over it because I know. Okay. Histogram. These are examples of a simple frequency distribution using a histogram. With a histogram, do you notice how the bars are slammed up right next to each other? Right? So this indicates that one goes right into the other. Okay? Notice there's no gaps there. They're right next to each other. Okay? Children's height in inches. Okay? Height, weight, speed. Because the type of data we're collecting necessitates that we're going to make a histogram versus a bar graph. Okay, remember how we talked a lot last lecture about, yes, you are the statistician, yes, you are the lecturer or the researcher, so you get to decide what kind of data you collect. But once you decide what kind of data you collect, then it decides for you what kind of statistical analysis you get to run, what kind of charts you get to use when you disseminate your data, right? So if you're going to collect data like this, right? So height, anything on a continuous line, right? Time, you need to use things like a histogram or polygraph. Okay. So how you show visually is you make those lines come right next to each other. Okay. You can also use a polygon. It gives the same feeling. Again, you're going to list all the numeric scores on the x-axis, but this time you're going to draw a dot above it. So instead of using like bar graphs, or I hate saying that because a bar graph's different than a histogram, you're now going to use dots, and then you're going to connect the dots using continuous lines. So it kind of looks like this. Okay. So for a simple frequency distribution, if you notice the little dot is right above the line. So what this is telling the reader of this graph is that every score is accounted for. Every score is counted. This is a simple frequency distribution polygon. Okay. Again, if I'm going to count how many people are in this study, I would go with my F's and I would count, okay, I had one person score a 6. I had 2 people score a 5. I had 2 people score a 4. I had 4 people score a 3. I had 2 people score a 2. I had 1 person score a 1. So I would add 1 plus 2 is 3, plus 2 is 5, plus 4 is 9, plus 2 is 11, plus 1 is 13. Okay. A frequency distribution polygon for group data. Look at where the dot is now. See how it's right in between the numbers? I have a little arrow there. So in between 4 and 5, if you see that the dot is hovering, right, in between there, that's going to tell the reader, that's going to tell the person you're presenting to that, yeah, the person could have scored a 12 or a 13. You had 4 of those kiddos in this study. Yeah, you had 5 ninth graders collect 10 or 11 seashells that day. Okay. So up until now, we've been talking about when researchers, you, the statistician, you, the scientist, have been collecting interval or ratio data. But that's not all the kind of data you can collect, right? When you collect nominal and ordinal data, you have to use different kind of graphs. They're not better or worse, they're just different. For non-numerical, so again, think names, think categories, you need to use different types of graphs, right? And one of those kind of graphs are bar graphs, okay? It looks a lot like a histogram, but now instead of the little bar thingies being right next to each other, you're going to have spaces. And those spaces indicate discrete or categorical data, okay? So when we talk about things like personality type, right? So you can have an A-type personality, you can have a B-type personality, you can have a C-type personality, right? So in a classic A-type personality, these are your high-strung, on-time, leaders, quick to anger, quick to be on time, quick to, I don't know, yell at traffic, that type of stuff. You always want an A-type personality person to be in your group because you will keep deadlines, you will have everything on time. You might not like them, they don't care. You will get a good grade on that assignment. Okay. B-type personality, they are funny, they are relaxed. They might show up to every meeting, they might not. They will probably always be late, but they'll have donuts. You'll probably like them most of the time until they drop the ball. But they won't be stressed if you like them or not. They don't care. Now, you can have an A-type, and you want them in your group, right? Because you can't have all A-type personalities because they'll eat each other. You can't have all B-type personalities either because nothing will get done. Okay. You can have an A-type personality. You can also have a B-type personality. But you can't have both. So that's what we're talking about with nominal data. It's not good or bad. It's just different, right? So again, that space in between the bars, note, tell the reader, tell the person that you're reporting to, these are discrete variables that I'm reporting on. Okay. When a population is small, it's okay to report on each score. When you're making a histogram, you're making a bar graph, whatever. When the population is large, scores for each one of the members aren't possible. So that's when we start doing relative frequencies, or what we call like grouped frequencies, and that's when we start using smooth curves, right? And these smooth curve data points are really to kind of indicate where most of those exact scores would be, okay? The most classic term for this is called a bell curve, although that's kind of a dated term now. We call it now more of a standard distribution or a normal distribution. In instances where we have a lot of data about people, they're symmetrical because in most attributes, characteristics on humans, we all fall into a normal distribution on physical characteristics, on intellectual characteristics, on personality characteristics, right? Even on reaction based on what kind of instances you place us in, okay? So this is what a normal distribution looks like. So this is intelligence, right? An IQ test. So when we get into our lesson 4 and 5 and 6 and 7, we're going to dive a lot deeper into this. But at this point, I just want you to just take a look at the shape. Okay? So as you can tell from the shape of this distribution, most people have an IQ score of around 100. Remember, what we know about frequencies, that's the whole theme of this lecture. Frequencies, occurrences, count, right? How many tally marks? How many people show up to this? So again, on the y-axis is your frequency, is your Fs, right? You notice lower score, some people have a low IQ, and the frequency peaks around 100, and then it starts to go back down again. It doesn't mean the IQs are going down, it means the frequency is going down. Symmetrical means the left side looks just like the right side. Or if you took a piece of paper and you folded it in half and you opened it back up, it would look exactly the same. Meaning, all the humans on the planet Earth, most of us have an IQ score around 100. Some of us have an IQ score of 85. For every person that has an IQ score of 85, exact same percentage of people walking around with an IQ score of 115. Same thing if you keep going down to the left versus the right. the same percentage of people that have IQ scores of 70, about the same percentage of people that have IQ scores of 130. Okay. Now, the terminology, how we refer to people that have an IQ score below 85, below 70, or above 115, or above 130, change, depending on what year it is and what country you're standing in. The percentages don't. Year after year, the numbers always fall like this. And there are some, what we call like tender spots and sweet spots, right? And again, we'll get into that a lot more in lectures starting around 4, 5, 6, 7. Okay, but just look at the shape of this. This is symmetrical. Okay. Not all distributions are symmetrical. So far left-hand side, you have a symmetrical one. Again, meaning the left-hand side looks exactly like the right-hand side. You can also have a bimodal distribution. So if you take a look in the top right-hand corner, that one is symmetrical also, but there's 2 peaks, right? So again, if you took a piece of paper and you fold it in half, it would be symmetrical. It would be perfect. This is traditionally the grade distribution of online classes. A's and F's. Very few C's. Very few D's. Very few B's. Recent, because of COVID, is different, but traditionally this is the grade distribution of online classes. We also have non-symmetrical skewness. Okay, so bottom left-hand corner, you have a positive skewness. So think number line. Remember, so you have a number line. In the dead center, you have 0. On the left-hand side, you have negative numbers like -1, -2, -3, -4, right? On the right-hand side, you have positive numbers, +1, +2, +3. It's going to sound silly, but if you act like it's an elephant, elephant is big, tail on the elephant is little. Which way is the tail facing or wagging? That will tell you if it's positively skewed or negatively skewed. Okay. So if you place the elephant on the number line, which way is the elephant tail wagging? Positive does not mean good. Negative does not mean bad. It just means which way is the data skewing. Okay. So if you think back to like introductory psychology, and you learned about like operant conditioning and classical conditioning, and your professor was probably very nervous about using words like good and bad. It was always like, or positive versus negative conditioning. It was always like good or bad or punishment, right? So same thing here. Just because something is positively skewed doesn't mean that it's good data. And just because something is negatively skewed doesn't mean that it's bad data. Okay. If I have student loan debt data, right, and I have it positively skewed, that's not good, right? That means that more people in my data set, the frequency, the number count, is piling up on that y-axis really, really hard. So again, think like an elephant is sitting on your number line there. Which way is the elephant facing? Which way is the little tail wagging? If it's wagging towards the positive end of the number line, it's positively skewed. If the elephant is sitting on the number line and his little tail is wagging towards the negative end of the number line, it's negatively skewed. Positive does not mean good. Negative does not mean bad. So researchers describe a distribution using words versus just drawing it when we report it, because vocally we can report it and everybody knows what we're talking about. And here's just some more examples. So top left-hand corner, you have a, right? So if you think about the elephant and its little tail, it's positively skewed. So frequency, again, y-axis. And here's the yearly income, and this is the age. Or sorry, yearly income, this is the dollars. So you have some people making, what is it, like 70,000, 105,000, very few people making 210,000. It's positively skewed. Not great though, right? Very few people making 210,000. One on the right-hand side, so this one's a negatively skewed, right? This makes sense though. Number of people retiring versus the age of retirement. Very few people are going to retire in their 20s. Most people are going to retire the later they are in life, right? Okay, so really quick, what's the shape of this distribution? Positively skewed.